What we're doing today, I'm not doing it. So what we're doing today is wrapping up just a few ideas about the harmonic oscillator, kind of relating it. So we really finished everything we needed to talk about the harmonic oscillator with the conceptual ideas of the harmonic oscillator. But there's a way we can relate it to things that we're familiar with, thinking about spectroscopy. And this is one of the first things that we can actually apply to the ideas of spectroscopy, and that's kind of nice. I have the particle in a box up here just as a reminder, and then we're going to get into the rigid rotor, and we'll see that there are some things in the rigid rotor that are parallels to the harmonic, no, not the rigid rotor, particle in a ring. Rigid rotor is the three-dimensional version of that we're not doing today. We'll get to that eventually. But we're just going to look at a particle stuck in a ring rotating along a ring path instead of a straight line. And that will get us started to think about this idea of angular rotation and how we deal with it. So that way next week we can get into talking about the idea of a three-dimensional object rotating around. But first, talking about the harmonic oscillator, we said we could do this thing where we have the wave functions. We again kind of got the wave functions just by saying someone else already solved the problem. We could go through the normalizations. We noticed that there needed to be some Gaussian exponential function to make it so it crashed out to 0 both directions. And then we said to have more than one answer, we're going to have some polynomial in there that can generate additional answers. And so that's the equation that we got. We can write down the equations for the Hermite polynomials. They're given on the equation sheet. We have some parameters that are defined to simplify things, and some defined to make it so we can talk about objects kind of attached to each other vibrating, rather than just having something attached to a wall. And that's the reduced mass. Regardless, we get this idea of energy, where V is a new counting number that goes from 0, 1, 2, 3 all the way up. And we have V plus a half h bar omega. So as V goes up, the energy of the harmonic oscillator, that vibrational energy, goes up by some h bar omega. With some floor, when V equals 0, we've got some minimum energy possible. Now, the thing that's kind of interesting, to get this into the scope of spectroscopy, we need to think about how light would interact with this. Now, that actually involves time-dependent quantum mechanics, and we're not doing that yet. But we can generally remember the energy of a photon. Ooh, do you remember what the energy of a photon is? Tell your neighbor loudly. Yeah, hc over lambda. Right, so if we had the energy for a photon, that's the Planck's constant times the speed of light divided by the wavelength. And the other thing that you might remember from the past is that the change in energy of an atom can be related to the photon energy being absorbed or emitted. Sometimes you put an absolute value there to be like the change in energy, because the atom could be gaining or losing energy, but the photon always has to be positive energy. In this class, we'll just do it in terms of the logic of recognizing whether it's absorption or emission to fix our sign. Now, if we're looking specifically, so we could do this. This is part of one of the homework problems. Did this for the particle in a box, looking at how different conjugated carbon systems, conjugated pi systems, could be used to talk about this absorption and emission phenomena between different n levels. We can do the same thing for the harmonic oscillator, looking at this difference between different V levels. But the harmonic oscillator works out in this really interesting way, where if I do, looking particularly at vibrational energy, if I do delta E equals some higher level, V plus 1, minus some lower level, V, we always get h bar omega. Now let me show you why, and I'm going to do it two different ways. First, I'm just going to do it with fixed numbers, right? So for example, say that we're going to V equals 2. Wait, let me think about this. If we're going from V equals 2 to V equals 3, well, that's not how you write that. So if we have V equals 2, we'd have our delta E equal to V plus a half plus 1. So this would be 3 plus a half h bar omega. minus 2 plus a half h bar omega. Then if we do the subtraction, if we put this all out, we can take the h bar omega all the way out. And so we can have 3 plus a half minus 2 minus a half h bar omega. Right, just a quick little rearrangement, and you can see the plus a half and the minus a half will cancel each other out every time. And so if we're just stepping between one thing, we're going to have 3 minus 2. That's just h bar omega. We could do the same thing if v equals 5. Right? The exact same math is going to come out. You're going to have 6 plus a half h bar omega minus 5 plus a half h bar omega. The 1/2 is always going to cancel out. And the fact that it's a v plus 1, just doing a step between two energy levels, you'll always get h bar omega. If we do this generically, it again comes out the exact same way, where you're going to have delta E equals v plus 1 plus a half h bar omega minus v plus a half h bar omega. Factor everything around, and you're going to have v plus 1 plus a half minus v minus a half h bar omega. And the negative v and the positive v cancel out. The positive a half and the minus a half cancels out. And you just get h bar omega. Why is this neat? Well, remember, there's a couple things that are interesting here. Omega has information about the relative masses of the particles we're looking at, and this restorative force constant. For us, this will allow us to look at diatomic molecules, and this will give us information about the behavior of the bond between the two molecules. This will be kind of like a bond strength term. It's not exactly bond strength, but it's that restorative force that's very closely related to it. So we can use this idea of the delta E equals h bar omega and hc over lambda to actually calculate things. Let me make sure I write this down correctly. Oh, you know what? I write this down in a different way in my notes, so let's just do this as well. It's usually done in terms of frequency, so hc over lambda, h nu, same. 1 through 5, familiar with the idea of wave numbers? It's just a unit. It's inverse centimeters. You see it a lot in IR spectroscopy and things like that. It's because the frequencies are all really large, and so you just divide by the speed of light in centimeters, and you get reasonable numbers between 100 and like 5,000. So it's a difference in units. But what we can do here is we can essentially use these two things, and we can have h nu equals h bar omega. Right, so our frequencies are related to each other. Now, if we know the definition of omega to nu, this shouldn't be surprising. The definition of h bar, I think I mentioned the first day. But let's see how this works out. So this is going to be h nu equals h over 2 pi square root of kf over reduced mass. And this allows us, we can cancel out the h, and this gives us a way to relate the frequency, the vibrational frequency, to things like the force constant and the reduced mass. So if we could measure that vibrational frequency, so if we knew what molecule we were looking at and we could measure the vibrational frequency, we could figure out information about that bond's behavior. Something akin to its strength, or how much it resists being pulled back and forth, its rigidity or more. This gives us some way where we can start to measure those sorts of things. Using spectroscopy, something that we can use, to look at these energy parameters, these parameters about the molecule that are a little bit harder to directly observe. We can also start to imagine what happens if isotopes are involved, because having an isotope change, one of your masses changes. You can change that reduced mass. Some places we see that really dramatically. For example, switching from hydrogen to deuterium, where you're essentially doubling your mass of one of your particles. That can have a really large effect. But if you're going from like chlorine-35 to chlorine-37, you can see a really small effect. But you still see an effect, and so that's why sometimes in spectroscopy, you'll get like isotope-based doublets, kind of extra things in there. And we can actually explain that by calculating the frequency for one isotope and the frequency for another isotope. How well does this all work? I'm sure you're wondering. So when we look at this, if we did a plot of the harmonic oscillator, no, that's not the center. If we did a plot of the harmonic oscillator, we would have evenly spaced levels, starting with a v equals 0, which is not at the 0 energy because of that plus 1/2. And then if you can pretend with me that I could draw even levels. Right, and it would keep going up and up. But in this situation, you can essentially have an infinite number of levels. You could put in an infinite amount of energy and still have a harmonic oscillator. Now, that should sound silly to you in terms of chemistry and spectroscopy and molecules, because you can't put in an infinite amount of energy in. You also can't push the atoms so close to each other that the nuclei bump. So it turns out that this side ends up being way steeper, and then this side ends up leveling out. And there's a certain plot for this. The Leonard-Jones potential is the one that is typically used to model molecular behavior. It works out way better than the harmonic oscillator. You have this term that goes off towards infinity as the nuclei get too close to each other. You have this term that goes off, that levels off as the nuclei fly away from each other. So if you get the nuclei too far from each other, they don't interact anymore. But in this small area down here, in that small area where you're at low energies and only displacing a couple levels, the harmonic oscillator actually does a really fantastic job modeling molecular systems. So it turns out the harmonic oscillator works pretty darn well when we're in that environment. Questions? That was okay? Question, yeah?
I don't know if this is out of the scope of what we're talking about, but how would we know whether or not it falls into relating to the harmonic oscillator being good?
Oh, so anytime we're at low V levels and low energy, the harmonic oscillator will be good. So that is to say, as long as we're in those low V values like 0, 1, 2, 3, 4, 5, we're probably in a pretty good approximation. If we go up too high, we know that we're going to get to this point where we should be hitting a ceiling of some sort. Question, yeah?
So if you, like, if your energy level gets too high, that energy level stops being quantized?
Yeah, essentially what happens is, as your energy levels get too high, that vibration essentially becomes such that the molecules fly away from each other. And so they're not interacting anymore, and so you don't have a restorative force anymore. So it works until you break the bond, and then there's nothing to pull the nuclei back towards each other. Other questions? Okay, so the other piece we have to talk about, it turns out that talking about a diatomic molecule vibrating usually also involves, that's not the only motion it can do, it can also rotate around in space. Now, rotating in three-dimensional space is a little bit complicated. We're going to get to that sometime next week, but we can start with just a simple picture of rotation and start talking about how we can lead up to this idea of three-dimensional rotation by just considering So we can consider a 2D plane rotation with a fixed distance. That is to say, if I've got, okay, now this is the part that I'm always bad at. I actually want like a whiteboard compass because I can't draw circles. But I'm going to try. I mean, I know it's a circle, but I can tell it's not in the middle and everything. So we're going to have this situation where there's a particular distance, r, and there's a particular angle, phi, that can rotate through. The particle is going to be stuck at that distance on that ring. This is sometimes referred to as particle on a ring. So it's going to be stuck rotating in that distance. We have this particular restriction. If this is our x values and our y values, we're going to have x squared plus y squared is equal to some constant squared. Of course, I'm going to call that constant. I'm going to call that constant r squared because I know where this is going. So I've got that distance. Now, this means we're going to have to think about multidimensional Hamiltonians. So our Hamiltonian in this case can be written in terms a couple different ways, but we can just do a p squared, notice no subscript on this one, over 2m, which is equivalent to saying negative h bar squared over 2m del squared, which is equivalent to saying negative h bar squared over 2m d by dx squared plus d by dy squared plus d by dz squared. Sorry, I went to the edge of the board there. Right, so this del thing is, do I have the name right? Laplacian operator? So that Laplacian, that del squared, is the 3D derivative operator. So it's doing the derivative of x squared, y squared, and z squared. Now, if we're limiting ourselves to just x and y, this z term should drop out. So that z term is going to drop away. And we're going to end up with just dx dy. This might make us a little bit unhappy. Right? So I'm going to have a Hamiltonian for this of negative h bar squared over 2m d by dx squared plus d by dy squared. After we limit ourselves to the xy plane. Right? Now here's why I'm like, oh, this might make us unhappy. Can I do separation of variables in this situation where x and y are related to each other? Right? They're stuck in that ring. I can't separate x and y. X and y are fundamentally related to each other in this situation. Because my ring is not solely along the x-axis or the y-axis. So that means we're in trouble. Or we pick a new coordinate system. So we switch our axis system. We've seen this before. Right? We saw this is kind of like what we did with the particle in a box, where we were using sine functions. We were like, that wasn't so great. Let's use e to the ix functions. Here we're using x, y, z vectors, right? Those are the functions we're using. We're like, those don't look so great. Let's try r, theta, and phi. Where, careful with which classes you've taken this. I'm using phi as the angle in the xy plane and theta as the z to, which would that be? The z through x to z plane. So depending on which class you use, theta and phi get defined different ways. Some people like to use theta as the one for the xy plane. The way I remember it is theta is the tilt away from z, and phi is the phase in the xy plane. Theta tilt makes sense to me. We'll get to that more in a little bit. Right now, we're not going to have to worry about the theta tilt because we're going to restrict ourselves to just talking about the plane. But there's a couple things we can do, we have to define in order for this to work. Okay. X is going to be r sine theta. Ooh, cosine phi. Y is going to be r sine theta, sine phi. And z is going to be r cosine theta. Where theta varies. Okay, how do we do this? Theta is, where did I write it down? There we go. There's two different ways to think about theta. Theta can be from 0 to pi. Some people do it from pi over 2 to negative pi over 2. Comes out the same way. Phi is going to be from 0 to 2 pi. Right, so phi is going to be this thing rotating through the entire 360 space. Theta, I don't have it drawn here, but theta is the one pointing out of the board and then tilting into the plane of the board and then back away. Okay, so theta is that one tilting that direction. With this definition of how we relate x, y, z to r, theta, and phi, you can also write equations for r, theta, and phi. They're a little uglier. But we also end up with volume elements. Right? So when we do our integrals and our derivatives, we get these extra bits because dx, dy, dz, that's on our xy coordinate, that's perpendicular to each other. R, theta, and phi are technically perpendicular to each other, but the volume relates in different ways. dr, r d theta, and r sine theta d phi. So when we want to take integrals, these are the volume elements we need to use. Now that's not going to be important to us today, but I like to repeat myself for these things that come back and haunt us over and over again. So I'll mention these again when they come up, but there they are at least the first time. Okay. We're going to restrict ourselves. I'm going to erase this bit so I can keep working over here. So, goodbye Leonard Jones. So when we restrict ourselves to just be in the xy plane, that would mean essentially theta is equal to pi over 2. And that gives us some simplification in these things. What's cosine pi over 2? 0. Okay, I was like, wait, did I get this wrong? Okay, so z is going to be equal to 0. That makes sense, right? That means we're in the xy plane. Z has no values. That's what we were expecting. X is going to be sine of pi over 2? 1. So we're just going to have r cosine phi, and y equals r sine phi. Again, this is specifically when we are restricting ourselves to the xy plane. So we're fixing our theta value to be a specific value. So we're restricting our system in that way. Here's the gnarly part I don't want to do. So I'm gonna write this. There's a really long process in the textbook. I actually don't even know if the textbook does it fully, but in several textbooks there's a PDF on Canvas as well. We now need to write d by dx squared and d by dy squared in terms of r, theta, and phi, which means taking a bunch of second derivatives, plugging in these values, and then applying chain rule over and over again, and then recollecting terms to simplify. Here's how it works out. So I'm gonna show you the kind of the end of the story, if that's okay. So we're gonna have our d by dx squared plus our d by dy squared, and that's going to go to d by dr squared plus 1 over r d by dr plus 1 over r squared d by d phi. I think I forgot a squared. I definitely forgot a squared. On that. Squared. Okay. Since, again, we have two restrictions, we have our theta restricted, and we also have a fixed distance. So those two front terms just go to 0. Because if I've got some function, I'm taking the derivative with respect to r, but there's no r piece, those things are just going to go away. So that means, for this restricted case, where I'm restricting my theta and I'm restricting my r, I just end up with this 1 over r squared d by d phi. So my Hamiltonian in this case ends up being negative h bar squared over 2m r squared, that's a typo too, d by d phi squared. Notice I'm doing the script r's when I'm doing the multidimensional derivatives. When I get back to the single dimensional derivatives, I just go back to the straight derivatives. Question?
What's WRT?
With respect to.
Okay, thank you.
I just didn't feel like writing it out. Question? Yeah?
Sorry, can you go over one more time why the derivative goes to 0 with respect to r?
If we are restricting our situation so that our function, the r is just a constant value, then the derivative with respect to a constant just becomes 0. Question further back? Same one? Okay. So our Hamiltonian for this, after all of that crazy math looking at that multidimensional stuff, actually ends up being relatively simple and pretty similar to what we saw for particle in a box. And that shouldn't be entirely surprising, because particle in a box is xy. Particle in a ring is just taking that same thing and flipping it over so the ends are touching. So you get a ring instead of a box. Particle in a box, particle in a ring. The physics of this should actually come out really similar. We should see a lot of similar ideas. We do end up with this extra term of r squared that we didn't have in the particle in a box because of the coordinate system change. That's going to work out okay. So when we set this up, of course, Hamiltonian by itself doesn't make much sense. So what do we do whenever we have a problem in quantum mechanics? Step 1, we define the system, giving our constrained stuff, talking about it in three-dimensional space. Step 2, we define our Hamiltonian. Step 3, we use the Hamiltonian to solve for the wave functions. And then step 4, we can ask all kinds of questions about the system once we have the wave functions. So we can go ahead and set this up. Our good old friend, let's just do this in blue still. Yeah. H psi equals E psi. Same old, same old. Right, where I can plug that in, I'm going to have negative h bar squared over 2mr squared. Tell your neighbor one or two functions that would solve this differential equation. Okay, I heard most of them up at the front. I'm hoping you in the back said this too. We're going to end up with a couple different things. Sine functions should work. Cosine functions should work. E to the I functions should work. And e to the positive I functions should work. So some sine of phi, some cosine of phi, some e to the I phi, and some e to the plus I phi. Right? All of those things should work. Right? So we've got a lot of different options. We also, hopefully at this point, recognize the fact that we can relate sines and cosines to the e to the I phi's through that Euler equation. So we really just have to pick the sines and cosines or to the e to the plus I, e to the minus I, and work with one set of those functions, not all of them at the same time. I'm working backwards on the board today. This is weird. I'm going to erase the stuff about the delta E. I guess maybe it's going to make sense that I'm working backwards in just a moment. Okay. So we can do some rearrangements here, and we can get d by d phi squared of psi is equal to 2mr squared e divided by h bar squared. Did I forget anything? Oh, yeah. Negative psi. Keep in mind this m, I'm going to do something that's a little bit strange because I'm going to have two m's in this, and there's a couple different ways that people rewrite this. There is the, there we go. So people rewrite this 2mr squared as I for the moment of inertia. Oh, not the 2mr, sorry, just the mr squared. I'm half convinced they do that just to get rid of the extra thing, the extra r's. And then they take this entire chunk, oh, not in blue again. Then they take this entire chunk here, and they say this is going to be equal to some constant squared. Now, we've already used k, we've used k a couple times, we've used n a couple times. The letter that's used for this is ml. M subscript L. And there's kind of a conventional reason for that that we haven't gotten into yet. For now, this is just ml squared. This combination of constants gives us that value, m sub l squared. This means our function some normalization constant times e to the I ml phi. Right, and we can prove that. If this thing is rewritten in that way, where I've got d by d phi squared, or d by d phi squared of psi equals m sub l squared of psi, this is going to give me an I, then a negative, then two i's, that gives me a negative, and I'm going to get an ml squared out front. Question?
Where did the big I go?
The big I is tucked inside of the m sub l. Right? So the m sub l includes that big I inside of it. Let me rewrite this two different ways. So we would essentially write this as dV phi psi is equal to negative ml squared of psi with m sub l squared equal to 2 IE on h bar squared. And then with this, it becomes really easy to see psi is going to be equal to some normalization constant times e to the I ml phi. Question?
So in that case, like the function we're using that should work is e to the negative I phi.
Or positive I phi. So we can actually do this one, or we could also do plus e to the minus I m sub l phi. Right, either one should work. We could have both of them added together to give us a more complete answer, because I comes down, I times I is -1, negative I times negative I, also -1. So we're preserving that negative sign out front, either one we choose. This is usually the function we write down for the particle in a ring. The thing is, here, I'll write them both down. And we end up with a really similar situation to what we saw with particle in a box, where essentially this one corresponds to clockwise rotation, this one corresponds to counterclockwise rotation. The restrictions on this, right, I haven't talked about the restrictions on this yet, and that's kind of an important bit here. There is a boundary condition, which is going to limit what this m sub l can be. Right, and the boundary condition is kind of weird. If you've got a ring, where's your boundary? Whenever it loops back on itself, it needs to be the same value. Right, it needs to be single value. So whenever it loops back on itself, it needs to be the same value. So psi of phi better be equal to psi of phi plus 2 pi. That better be true. That's our boundary condition. These two things are equal to each other. And it gives us a nice restriction to the m sub l values that we have. Because when we plug this in, we're going to have, not worrying about the normalization constant for a moment, I have e to the, I'll do it for the positive one, I m l phi is equal to e to the I m l phi plus 2 pi. And when I have that positive, when I have that addition in the exponent, that's like two functions times each other. So I can rewrite this as e to the I m, that's supposed to be a subscript L. E to the I m l phi, e to the I m l 2 pi. And so the question becomes, kind of the same thing we saw when we were looking at particle in a box. We're just like, okay, when is this true? Just like we were like, when is sine of 2 pi, when is sine of n pi 0? When is the sine of e to the, or when is e to the I ml 2 pi just equal to 1? Because I don't want a sign flip, I don't want anything like that. It turns out, though, with this function, m sub l, for this to be true, m sub l could be equal to 0, like e to the 0. That should work out great. Turns out, if you plug this into your calculator, it could be plus 1. It could be minus 1. It could be plus 2. It could be minus 2, and it could keep going. We usually write this down. I didn't want to write it down this way right away. Right, so 0, plus 1, or minus 1. We just write it as plus minus 1. Plus 2 or minus 2. Plus 3 or minus 3. And so on and so forth. And right now, with just the particle in the ring, there's no upper limit to this. This could keep going up to any value. And it essentially tells us how fast is it rotating around one direction or the other direction. And whether it's positive or negative, we get this kind of restriction in our possible m sub L values. Now, this means, let me do one more thing. We can write down rigid rotor solutions over here, where our psi is going to, I didn't solve for the normalization constant yet, but we're going to have some e to the I ml phi. Our energy for that m sub L value, I can just rearrange this thing, is going to be m sub L squared h bar squared over 2. I'm going to uncouple these things for a minute. Right? 2 times mass times radius squared. Look at how similar that is. Right? Makes sense that these two things look similar. Box, ring, box, ring. Question?
I'm confused. I thought we were learning particle in a ring.
Oh yeah, sorry. I keep going to rigid rotor. That's what it leads to. This is the first step to doing rigid rotor. That's why I keep making that mistake. If I was going to talk for another 30 minutes, we'd go right into rigid rotor. So I'm going to stop here after I answer questions. Yeah?
What did you mean by when you said like when m sub L is equal to 0 plus or minus 1 plus or minus?
So this in order for this boundary condition to be met, where as the particle goes around the ring, when it gets back to the same spot, it's the same value, that works only when m sub L are these values, because when I do this condition of the phi plus 2 pi, that's like an e to the I phi plus an e to the I ml 2 pi. And so the question becomes, when is this chunk? So when is this true is really just asking, when is this thing equal to 1? So that thing is equal to 1 whenever we have these conditions met. And so by putting this boundary condition in of saying it's got to be the same thing as it comes around, we get these values out. And we get restrictions on what our energies can be. We get restrictions on, it can't spin around at any speed. It's got integer value speeds, but spinning one direction and spinning the other direction is pretty much the same energy. It's just which direction the vector is pointing. Question?
Just trying to relate this to like something I can think of. Like, is it like just electrons, or what are we talking about? Like
So it works for many different things. As we go to the idea of the rigid rotor and the three-dimensional object rotating, you'll see this being applied to electrons caught in a radial potential. So we'll see it there. You can also, the more simple version is just a diatomic molecule rotating around in three-dimensional space. Right, or sorry, rotating, okay, so this is particle in a ring, not rigid rotor yet. So it would be like an HCl, where the Cl is really heavy and the H is just kind of spinning around it, stuck at a particular distance. And that would be a relatively good approximation of this if it was only spinning in one plane, which we know can't be true. It's going to tilt out of that, and we'll get to that next time. Other questions? Yeah?
What's the reason that one's 0 to pi and the other's 0 to 2 pi?
So it turns out that for this phase angle, we have to go through the full circle to get all of the three-dimensional space. But if I have a vector rotating in three-dimensional space here, I only have to go through half of the space with my tilt. And if my phase is over here, I can get that other half of the circle. I don't need this one to spin in a full circle. Otherwise, I'd be double counting that part of the circle. Or sorry, that part of the sphere, three-dimensional. Yeah?
Does this branch of this math have anything to do with it would be an addendum to it, but how you get the J splitting values in a magnetic field?
It's precisely. Oh, magnetic field, yeah. Right, so
you said it's spinning one direction has the same energy as another one, but
yeah.
That's not true in magnetic.
So, and the place where I'm thinking is you're talking about J coupling, not the J splittings in spectroscopy. So this relates to rotational spectroscopy, not NMR spectroscopy. So in, and also, the splitting's going both directions, right? It's not going to be which direction it's spinning, it's going to be the difference in the energy levels anyway. So if it's spinning one direction, you get the difference between the two levels, you'll see something. Does that make sense? And also, to be clear, this is rotational, this isn't quite yet magnetic. Other questions? Yeah?
Why did we choose e to the I and
I knew the math was good. So mostly because I wanted the math to work out so I could talk about the angular momentum and like the momentum in one direction or the other. I wasn't going to worry. I didn't, and I knew it would work out. Remember when we did the sign functions, it worked really, it also works well for the boundary conditions, right? So it's just making that choice. When we did the sign functions for particle in a box, it was the boundary conditions were really easy at the 0 and the L. But then we ran into trouble when we wanted to talk about the momentum of the particle. And it technically would have been easier if we went straight to the e to the I5 for the particle in a box, because we would have been able to do, the boundary conditions would have been a little bit more difficult, but we would have been able to go directly to talking about the momentum without having to do any tricks, mathematical tricks. Here, I already knew that I wanted to talk about the momentum, so I made that choice. And I also knew it would work out okay for the boundary conditions. Question?
M sub L, it's not spin, because like in Gen Chem we learned it as spin, right?
So this is, no, M sub S is usually picked for S, for spin, and that's particularly electronic spin. This is going to be related to it's going to be related to orbital angular momentum when we get to doing it three-dimensionally. And it'll be particularly the Z component of the orbital angular momentum, but we'll talk about that when we go to the three-dimensional case.
Okay, thank you.
Yeah. But yeah, it's moving in that direction.
Okay.
Other questions? Yeah.
Maybe a stupid question, but for the e to the I m sub L does that include both the x and y components?
Yeah, because when we rewrote, there's a way can rearrange this xy thing to talk about phi, and phi is going to have the x component and y component in it. Right, so it was this way that we redefined our coordinate system so that phi does have the x component and y component in it. But we'll usually talk about it in terms of like the rotational components. Other questions? Okay.